Okay, well, today we have travelled to Swansea, to the Bay Technology Centre, to visit a company called Ail Arian. And I'm going to be meeting the team. I'm going to be talking to James Claypole, who CEO?
Yes.
Yes, CEO of the organisation, and the team here. And we're going to be taking a look at a new technology which is targeting e-waste, which is getting a lot of news at the moment. There's a lot of regulation, standards, etc., starting to emerge across the world, looking at how electronic products will be managed at end of life. And this particular ink technology that we're going to be looking at today is part of the solution to that problem. So I'm going to start by opening with a very big question, really, which is, what question would engineers be asking themselves for your technology, James, to be the solution? And then if you can give us a sort of summary of what that technology is, where it fits into that process. But before we do that, could you just explain the name of the company? Where does Ail Arian come from? What does it represent?
So Ail Arian, it's an interesting story. So we are a Welsh startup. So it was important that we kept some reference to our Welsh heritage. So Ail Arian is actually a translation into Welsh for the term re-silver, or recycle, the shortened form then of recyclable silver, which is what we're all about.
Okay, brilliant. So back to that original question. What problems are engineers trying to solve that your solution and your technology would help them achieve?
So I guess the problem is divided up depending on which particular segment that we're looking at. So in general, it's electronic waste. As you alluded to, electronic waste is a huge global problem. And we're not going to pretend to change the recycling process because that's not my background. So what we're actually doing is taking a design for recycling approach to solve this particular problem. So yeah, I guess the overarching question is electronic waste, but the kind of then breaks it down a little bit more by segments. So printed electronics, electronic waste, the kind of recycling rates are sub 20% globally, which is pretty poor. But actually the printed elements, actually truly printed electronics, are even worse than that. So actually it can be as low as 0%, normally because the printed elements cover a very large area with a very thin layer of metallic compound. So actually that often ends up just contaminating plastic waste streams, and actually the plastic waste element that's sorted out of electronic waste. So that's an even worse problem. And again, this is more of the problem that we're trying to solve. And that aligns very much then with the kind of similar problem within smart packaging, in that you have smart packaging is really interesting. It has loads of fantastic benefits by being able to record in terms of digital product passports and actually understand what's going on, tracking, security, loads of benefits to having a smart packaging device. The biggest challenge then is it's completely at odds with the packaging and packaging waste regulations in the EU, which are all about creating a mono material construction so that you maximize the value of the actual recycled material. And I guess that goes back then into the general electronic side again. So from the recycling side, it's all about maximizing the value of the recycled material to make it economically worthwhile. So if you end up with loads of electronics contaminating your plastic waste streams, it reduces the value of the plastic, and it also means you're losing huge amounts of value then from the actual circuit components, from the actual conductive metals that are in there. And that's before you get to the point that there's a huge environmental impact from that as well.
Okay. So explain to our viewers, if we're taking a printed circuit board as the obvious example, how is that done now? How would it be done in the future with your technology? Where does difference actually lie?
Yeah, so at the moment, most printed circuit boards, your traditional sort of PCBs, are acid etched copper laminate. And it's a process that's hundreds of years old, and it has got more complicated and more exact, but it's still very much the same process. You still use caustic material in a subtractive process to remove the copper where you don't want it and just leave the tracks that you do. What we're doing is properly creating printed electronics. So our process, rather than being subtractive, is additive. So we're actually creating a circuit by putting down conductive material. This has, in itself, has sustainability benefits in that you're using less material, you're wasting less material, you don't use any of the highly corrosive chemicals that you normally use to actually acid etch the copper off in the first place. So there's benefits there. The challenge really has been that regardless of whether it was acid etched copper laminate or whether it's our material, at the end of the day, it all faced the same fate. It still went into the e-waste recycling streams, which are basically acid or burning to get the metals out, smelting to get the metals out. And that isn't the solution. So what we did was we looked at how we can change the materials that we put into that conductive layer to make it easier to recover it at the end of life.
And so talk us through the sort of specifics of that process. We're going to go down to the lab after we've spoken here and take a look at it. My understanding from what I've seen so far is that you're using a silver conductive element to the printed circuit board rather than copper. And it's designed in such a way that at the end of life, using a magnetic process, you can then withdraw that material from the circuit board, process that circuit board separately, and then recover that ink. Have I got that right?
Yes.
Yes. Okay. Give us a little bit more about how that works, because the last time I looked, silver wasn't magnetic, so there must be some magic in there somewhere. Yes.
Yeah, so this is it. So it starts with a silver conductive ink. So we call it a silver ink because that's what it's closest to. And it most closely resembles the traditional silver conductive inks that you can already buy. Yep. What we actually do is we use a complex particle that has a complex shape based around silver and iron. The advantage being that what we do is then we create a magnetic core to the particles.
Okay.
This allows us to create a silver that is magnetic,
right,
whereas traditional silver isn't. And that's all well and good. That's all interesting. It just means we use less silver in the inks, which has its own sustainability benefits anyway. But it's not, when we actually come to make the inks, when we come to make the things, it's not that interesting necessarily, without going down a rabbit hole there in terms of what's interesting about fun with magnets. But so essentially we print it the same way as you print any other silver conductive ink. Silver has lots of advantages because you don't need to sinter it. You can put it onto a huge range of substrates. So you can put it onto your traditional plastics, FR4s, PCB type material, but you can put it onto roll-to-roll coated PET. You can put it onto paper. Because it's not being sintered, you don't have that high temperature process. You have a relatively low temperature drying step to create that conductive circuit. So it kind of opens the door into it going onto a wider range of substrates.
Okay.
That's all interesting. Again, you could do that with other silver inks as well. What's really interesting about our material then comes at that end of life, as you said. It's all about recycling it, all about what we do in that recycling stage. So by breaking down the actual binders that are holding that silver in place, it allows us to use magnets to recover that silver material, fully separating it from the rest of the substrate, be that plastic waste, be that paper, card, fiber, FR4. We then remove that conductive material in a way that allows us to reuse it straight away. So we can take that conductive material we recover and turn it back into inks, kind of closing that loop on a circular process. But also then we're preventing that contamination. So we're not contaminating the paper waste streams. We're not contaminating the plastic waste streams.
Okay. So I'm going to re-summarize this in my mind. So you've got a ferrous particle, which is silver coated to give you that surface effect, which is then conductive and behaves like a silver ink would at the moment. That can be laid down on pretty much any substrate to create a conductive track. And you don't need to sinter it, so you don't need to heat it, so it can go onto paper and things like that. And I think later on when we go down to the lab, we're going to actually do some practical recycling of prints on paper, which will be fun. And then at the end of life, you can release that silver. You can then use magnets to recover it. And magnets, obviously, a standard process in the recycling industry. No need for any heat or anything at that point as such.
But not by the levels of
Not by the
industrial
same
standards. So
standards.
again, depending on the substrate we use the right blend of relatively mild chemicals to actually break down that polymer.
Right.
When we do it on paper, we can use water-based inks, and so we can use warm water to break that down. For some of the more industrial processes, we use relatively mild chemicals or chemical solvents matched to the particular polymers that we're using. So there's a pairing element there in between choosing the right polymers and solvents.
Okay. And then once the magnets have recovered that silver powder, that can then enter a circular production process where that can come back and be reapplied to new circuits and products. And because that's been removed, then hopefully you're into a sort of monomaterial process for recycling that plastic. So it should improve the recyclability of both those materials, one circular and one potentially circular.
Yes.
Okay, yeah. Excellent. Thank you very much. I know that there are two distinct markets for this that you're looking at. There's the electronics and PCB, but there's also then the packaging. Could you just give me a little bit more detail on the packaging? Because I think, again, when we're down at the lab, we're going to look at some shredded RFID type products and see how magnets can be used to remove that from one recycling stream. So just tell us why sort of intelligent packaging is on the rise, and again, where your technology suits.
Yeah, so intelligent packaging, smart packaging has loads of benefits. There's loads of really upsides to it in that you can track materials, there's loads of security, inventory, reducing waste through stock checking dates. On a very basic level, then you get kind of more advanced ones where you have more like GPS tracking for optimizing supply chains, digital product passports, but also then like temperature monitoring and conditional monitoring to actually really optimize that kind of what that packaging is doing, and it's doing so much more than just protecting or being a barrier around that particular product. The big downside, and there's only one really big downside, but it's a big one, is that it is completely in conflict with the EU's packaging and packaging waste regulations, which at the moment are set pretty high standards for the amount of other material in the actual waste streams, but actually that's going more and more. So actually massively reducing the amount of other material you can have in those waste streams with a view to creating mono-material recycling streams. Which is then, obviously, you can't have a mono-material recycling stream with smart packaging elements mixed in there as well. So what we can do is we can actually separate out using the magnets, again, quite common in recycling centers and things like that. You can use the magnets then to separate out the smart elements from the rest of the packaging. This means the rest of the packaging can continue on and be monomaterial while still getting all of those smart benefits from the actual smart intelligent side of it.
Excellent. Well, thank you very much. That's been, I think, a fascinating insight into the challenges that both the electronics industry and the packaging industry are facing, and that there are solutions and they exist. And we're going to go down to the lab in a minute and we're going to see them in real life. We're going to pick them up, make things, recycle things to prove to the world that this technology is real and is happening right now, and that organizations are buying into this, and that it solves those problems in both those sectors and probably more sectors over time. Now let's head downstairs into the lab and do some work.
Yeah, brilliant.
Thank you. All right, well, we are now in Ail Arian's laboratory, and I'm with James. And James is going to give us an excellent guided tour of this facility, talking us through the process of developing and testing and applying these particular inks. So we're going to start at this particular cell, which is where the materials are formulated, for want of a better word, I think, where the constituent parts come together, the resins, the silver powders, etc., as they start their journey through the process of test and evaluation. So I'm going to ask James now to start step one.
Step one, the start of our process starts with a resin. So all inks start with a resin and base, something that looks like this. The resin base is a combination of polymers and solvents. The idea is those different polymers and solvents give a different viscosity, but it also then gives, the polymers give it that adhesion to the substrate. So different polymers for different levels of flexibility, strength, lifetimes, and for different materials. To that resin base, we add silver powder. So this is a fine silver material. This is then dispersed into that resin to actually leave us with a conductive ink. Our conductive ink looks something like this. Once it's all been mixed together and very thoroughly mixed and milled, we end up with a conductive ink that looks something like that.
When you use the term milled, what does milling mean?
So milling for us is using something like this. This is a very small lab scale through roll mill. This allows us to test a very small amount of material. It allows us to kind of iterate our formulations without using vast quantities of material. What this does is essentially we put the mill in at the inking goes in at the back, and it's basically grinds down between these rollers. It makes sure we get a really homogeneous dispersion of the silver material within that resin. It also then breaks up any lumps, any bits that are a little bit larger are all broken down, so we end up with a very fine, very smooth, well dispersed ink.
We've mixed it, we've milled it to get the sort of consistency, I guess. What's the next step?
For us, consistency of the materials is really, really important, and actually the standards that we have are very, very high in terms of making materials that are of the best quality. So we actually use a rheometer. The rheometer is a scientific grade instrument designed to provide a wide range of rheological properties on the actual inks themselves. We use this both in our ink development to kind of guide our formulations to optimize the formulations for different processes, but we also use it as a quality control tool to verify the composition of our inks and to adjust for any changes in feedstock.
You're adjusting that formulation for different applications, I guess, different printing processes, different end application requirements. I know you're working in printed circuit boards as well as sort of advanced packaging solutions with RFID and intelligent sort of labeling. How many formulations do you expect? Is it likely to be a sort of standard catalogue of formulations plus custom? How do you imagine that working sort of in the field?
Yeah, so what we're likely to have and what we're working on is a base, effectively a starting point of maybe 5 or 6 different formulations that are, for want of a better word, a little bit more generic. So there'll be a water-based one, there'll be one that's solvent-based, there'll be one that's designed for plastic, or one that's designed for paper, one that's designed for wearable tech. And they will be a good starting point. The idea is then we work with the individual customers to refine a specific formulation for their applications then, normally based around a starting point. So the starting points give us something that's they can test that puts them in the right ballpark. Because at the end of the day, every application has a little bit of a different need. They're all a little bit bespoke. They have different minimum requirements, different maximum requirements for different areas in terms of roughness or viscosity or electrical conductivity. So we actually then tailor that formulation working with the partners to actually give them a optimized ink for their particular process and their particular application, normally based loosely around one of the ones that we had as a starting point.
Okay. And in terms of the variables you're controlling for, you mentioned there viscosity, conductivity, that sort of thing. What's that list of variables that you're controlling for?
Yeah, so again, this is quite a very long list potentially.
Right.
So there's the whole bunch of electrical properties then in terms of conductivity, which obviously affects your performance of your ink. Because you're talking about laying down a printed layer, you have a roughness element to it as well, and an ink layer, an ink film thickness. Then you have a lot of that's dependent then on the viscosity of the ink and the actual process. So the viscosity is more to do with the actual linking the ink with the right process. So different processes have different viscosity requirements. So a screen ink is kind of the viscosity of honey, and a flexographic ink is more like squash at times. But you've got a very wide-ranging types of viscosities. It's more about aligning it with the process to optimize performance.
And you've mentioned some printing processes there. Now we're going to, once we've finished at this station, we're going to step over to the to take a look at the screen printing machine you've got here. But it has got me thinking, because there are lots of different printing processes. How many sort of fundamental printing processes is this material aligned with? How many printing processes do you think it will be used with, and how do they differ according to applications?
So for us, the primary focus, our early focus, is on screen printing. Screen printing is really versatile. It's a fantastic process for actually putting down conductive material. It's quite forgiving in terms of a process, and it allows you to use quite a wide range of materials, and you can print with fairly small volumes of ink. The kind of next stage of development that we're working on is roll-to-roll flexography. Mm-hmm. Really, you're talking huge jump in volume then. So we're talking going from hundreds of grams of ink to kilograms of ink that you need to even start testing at that kind of scale. But you're also talking about much higher volume production as well. You're talking about hundreds of meters per minute potentially with flexography. Those are probably our kind of two target processes. There's some direct deposition type techniques as well. And the direct writing type things, probably staying away from things like inkjet. Inkjet has a number of challenges for highly particle heavy inks. It doesn't mean that we won't get there eventually, but it's definitely not our focus.
Okay. I was going to ask about inkjetting, but I had the same thoughts in my head that it's granular, isn't it? So it could be difficult. There is a process that sometimes is combined with screen printing that I've seen used quite often, which is sort of pad printing, tempo printing, where you might pick up an image that's been screen printed and then press it onto a product. I'm guessing that might be applicable.
Yeah, it's possible. A lot of the pad printing has very similar requirements to flexography in terms of the actual construction of the ink. The inks actually are, with some variations in the types of solvents you're using as well. So you have different types of fast and slow solvents, but it's very similar in consistency to flexo printing. Mm-hmm. And it's possibly maybe a development for the future for printing around curved surfaces. But then you get different ways of doing that, things like in mold decoration and things like that, which is another challenge, but you can do that with screen printing as well. So,
okay. Could you give us just maybe a couple of applications for flex and a couple of applications for screen? I'm guessing the obviously one for screen is printed circuit boards. Where else could that go? And then the flex type printing, where would that find itself?
Yeah, so for screen printing is pretty versatile as a process, but relatively lower volumes by comparison to, say, flexography. But it can be used in some elements of smart packaging. It can be used in circuit boards. It can be used in fast tech, those types of applications, and like wearable tech and things where you're kind of maybe making a smaller number of bespoke things. You can print huge amounts of things with screen printing if you just keep running the presses, but that's high. Once you go up to that next kind of volume level, you step up into flexography, and flexography is maybe more like printing hundreds of thousands of things. You're talking things maybe into the realms of things like biomedical sensors and into the more volume smart packaging things. So things like the RFIDs, where they're mass produced and volume produced, is more the flexographic side of things. But a lot of that development will come from screen printing initially.
And I'm just going to stay here for a little bit longer because I know you're very proud of this machine. You've given us a little bit of a tour of this already. Can you just describe what this machine does, why it's important, why it's here? Because I'm sure our viewers, lots of them engineers, will be fascinated in the capabilities of this bit of kit.
Yeah, so the rheometer is really a properly scientific piece of equipment. It is not often found in commercial settings as such, but the idea is that what it does is you can measure a very small volume of the material very, very accurately. So rather than just getting a viscosity for that ink, we actually are able to produce a report or produce information on a whole range of different properties. It allows us to understand actually what's going on in that ink, from not just the resins, the solvents, how they're all interacting, how they're interacting with the particles, how the change in the loadings of the different parts are all interacting together. And from that gives us a really good understanding of what's actually going on in that ink. It allows us to optimize the formulations for different processes with using the minimum amount of material at each stage. But then it allows us to quality control and really understand what is changing in those things, if anything is changing, and make sure we produce a really high quality product.
And would you, when you move to sort of volume production of these materials, would this be the type of machine you would use then, rather than in an R&D environment, but in a sort of quality control process? Would you be batch testing on this type of machine, do you think?
Yeah, so when we scale up, the idea is that we will continue to make the ink, and we will continue to take samples out at stages apart that to test. Essentially, it takes sort of 2 to 3 mils of ink to do a very thorough set of characterizations. So we can take out 2 to 3 mils from every batch, and we can really characterize that, ensure that we're producing a quality product every time.
Right. That's good to hear. One of the sort of big mega trends that we are looking at the Sustainable Engineering Alliance is the whole idea of right first time, reducing the amount of material, human effort, energy, etc., and reducing the amount of waste during that product manufacturing and commercialization process. So it sounds like this bit of kit fits that in terms of right first time.
Yeah, very much so. So because we actually understand what's going on in that, and because we need so little material to actually run the tests and to get the kind of information we need, we only need to make up 2 to 3 mils of every type of ink. As we're kind of optimizing that formulation for a particular process, it means that we're not having to make up enough to print every time and then throwing away huge amounts of material, essentially, that we've had to print to kind of understand whether or not one formulation is better than the other. Because we do a lot of that early vetting, essentially, with the rheometer, so actually kind of optimize that formulation before it goes anywhere near the press.
Fantastic. Now we're going to move on from here. Again, I know a lot of my viewers are in the electronics industry, so they'll be familiar with screen printing. But for those who aren't, we're now going to step over to take a look at the screen printing machine, which is always something fun to do. Right, James, I'm just going to ask you, having lowered the screen down, I can see the print profiles that are in place there. They in themselves look quite interesting. Can you just talk me through why you've chosen this print pattern and what each of these prints is sort of testing for?
Yeah, so this is very much a more generic test pattern, just to try and test the possibilities of what we're doing, but also kind of to give us some data on terms of performance. So we've got a couple of different features on here. The one is a mocked up of what an RFID might look like, or some form of aerial. The idea is that it just showcases what that pattern might look like. These are essentially a electrochemical biosensor for the electrodes for a biosensor and what that might look like. Then the ones from a scientific point of view or a research point of view that we're more interested in are these lines. They are printed at 45, 90 and 0 in relation to the print direction, because you get different performance then with where the screen runs back and forth. Yeah. So some inks will give you much better performance at certain angles relative to the actual screen print itself, which is why we kind of do them in different directions. Yeah, so what we started with, so we've got our screen, it's all set up. We checked the limits for the squeegee and the flow coat. So what we're going to do now is just load the silver paste in, just give it a little stir, and we're going to put it all down the one end, so it's all going to be there ready. Just the flow coat's going to spread that paste over the screen, and then the squeegee is going to push that, push the paste through the screen itself to give us the pattern. So now it's loaded, we're going to press the foot pedal down to action it. So the screen's going to drop down, the squeegee is going to come across and basically force the ink through the screen to give us our printed pattern. The flow coat's then going to come back across and spread that ink back over the screen, ready to go again. You can see it's quite a quick process, so you can quite quickly produce hundreds and thousands of things if you really needed to.
Excellent. Thank you very much, James, for your perfect demonstration of screen printing your ink. Right, so we have now been through the three sort of primary processes. So we've taken a look at the formulation and mixing. We've taken a look at the rheology prior to print. We've taken a look at the print process itself. So we've now got some printed samples right here, but also we have Hannah. And what Hannah is going to now do is take us through the real magic of this, which is how all of this is actually recycled. Because this is what this story is all about. This is what this technology is all about. It's all about getting rid of the e-waste problem that this world faces at the moment. And the secret to all of that is right here. And apparently I'm going to be the guinea pig for this. And I'm going to recycle it under the tutorage of Hannah. So tell me what to do. Let's give it a go.
So here we have our printed circuits that we've printed onto special seed paper.
Okay.
So what I'm going to ask you to do first of all is to just break those in half, just tear it into half.
Tear it in half, okay.
And then pop it into the hot water.
Tear it into quarters, shall I?
Yeah, that's fine.
Right,
There
so
we go.
that's it. Printed things
Yeah,
done.
pop that into
Any
there.
colours? Yep.
And here's a spatula, and
Okay.
you just need to start stirring.
Sorry, I'll stir
Just be careful because it is boiled water.
that. Yeah, that's right.
So you're going to have to stir that for approximately a minute.
Okay.
And what you'll start to notice is that that will start looking, as the children told me in the outreach program, like mashed potato.
Okay.
Once it starts to get to that consistency and the water gets very murky, that's when you can see that the silver ink has actually started to break down.
Okay. Starting to go cotton woolly.
So what I can do now is if
Yeah.
I just pop that magnet on the side, if
Yeah.
you keep stirring, what you'll start to notice, if you wanted to just tip that towards you slightly,
Oh, to me. Yep,
Yeah.
sorry. Yeah, okay.
you can see
Right,
that
yeah, I can
silver.
see it's starting to bind to the magnet.
Mhm.
Yeah. Gotcha. What?
Yeah. So now that
Well,
we've got that far, what you'll see as we tip that up,
yeah.
it's now separated all of the silver from the paper.
Yes. So hold that onto there.
Yeah.
Yeah.
Ooh. And then just put that into that.
Got it. There it is.
Okay. And now just give that a little stir.
Got
Okay.
it. Yeah.
And then we
That's
can
seed
take
paper.
some pots.
Uh-huh.
They come apart.
Stir, stir.
Don't
So
worry.
then in here, that is where the silver is attached to the magnet, yeah? And everyone's going to be asking, how does silver attach to a magnet the ability to hold on to that ink using a magnetic process
Yeah.
to separate that from the circuit board, the paper, the sensor, whatever it's attached to,
Yeah.
and then circularize that back into the manufacturing process. So there we are. I did it. Thank you, Hannah.
That's okay.
So the same thing as you were just doing then with the
Yep.
magnet,
Yep.
and this rather than being water, this is proper solvent.
Yeah. Okay.
But these are, again, so on a small scale, this is our cut-up cleaning rag that we just use to clean the press.
Yep.
So obviously, for those who know printing, it's really, really messy. Like large chunks of the stuff that you make goes out as waste. What we can do is we can take the cleaning rags as well, and we're going to mix this in with the solvent to basically free up those particles.
Yep.
Same process as you were doing, but
Yep.
on for a very different purpose.
Yes.
But again, we've then
Yep.
removed the bulk
Wow.
of the silver from the cleaning rags.
Oh, okay.
And what we're left with then is collecting the silver then
Yes.
from the actual manufacturing process. So it's not just
Okay, so it's not just the finished
it's not
products.
just the finished product, it's getting it back from every part of that process. So
Right.
even though printing's a messy process,
Yep.
we're actually not wasting that silver.
Gotcha.
That silver is coming straight back. We're going to turn that straight back into an ink then.
Okay. Yeah, fascinating. Yeah.
So this is what happens once we've finished breaking down the recyclable silver ink into water.
Okay.
And what you'll see with this is as I start to stir it around,
That'll start to pour away, I'm guessing.
yeah, so it starts now that it'll start sticking. So can you see just there
Yeah.
where it's all
Okay.
starting to
Yes.
stick to the magnet? And the more we give this a good shake, you can see all of that there.
Yeah, got it.
Yep.
Yep.
So that's an example of how we can separate what is the silver ink from the paper substrate.
Excellent. And
Yeah.
that's the iron core of that powder,
Yes.
which is then silver plated,
Yeah.
giving you that magnetic ability to withdraw that.
Yeah.
Gotcha.
So you can see it all in there then. And then when we have finished with the recycling experiments, what we are left with is something that looks like this. So this is all silver ink in there, and it's will just be mixed with some water from the children doing the experiment.
Yep.
And then we take this, then we give it a very good clean. And then this, once it's all dried out, then will be used to make a brand new silver ink.
Okay.
There's no further processing that it has to go through. It can just be reused.
Okay.
And yeah,
Brilliant. And as you explained earlier, the experiment that we've just done was designed as part of an outreach process that you've been running.
Yes.
Can you just give us a summary of how that's been working?
yeah, of course. So we really believe that sustainability starts with the younger generations. So we've been going and we've been telling the children all about electronic waste and just really, making them aware that they've got so many devices at home. They always want the latest device and what happens to the older ones.
Yep.
And then we've been, once we've finished that presentation, we've been taking them into another room, and we've actually been doing this experiment where we take the printed circuits
Yep.
and we transform them into wildflowers.
Brilliant.
Yeah, and they really enjoy it.
Yes.
So it's really good.
Yeah, that's fantastic. So they're actually getting practical, hands-on experience
Yes.
with a novel technology,
Yes.
which you see here first,
Yeah.
and then get a natural product at the end, the waste separated, and then they can grow those flowers from that paper
Yeah.
and see the results of their efforts.
Exactly,
Yeah,
yeah.
fantastic.
These are some examples. So we've got here some clear plastic, and this is an RFID that we printed using Ail Arian's ink. And then this one is some plastic with just a traditional silver RFID. And what we can do with ours is we can go through and we can actually separate all of the silver and all of the RFID out of this.
Okay.
And then what we are left with is just clear plastic waste.
Yep.
So this can be recycled, and there's no worry then that this is going to contaminate the waste stream.
Okay.
Whereas obviously with this one, I can roll my magnet around and
Yep.
there's nothing that's going to be stuck. So this would essentially go into the plastic waste stream, and it's all contaminated. Yeah.
Yeah.
So what would generally happen with this then is that this would be incinerated because they can't separate the
recycle.
plastic. Yeah.
Okay, so there, for example, if that was like a hard plastic being used for packaging,
Yeah.
and that was an intelligent label as part of a sort of product passport type
Yes.
type activity, that material is going to end up in some sort of shredder,
Yeah.
I guess, as part of that recycling process.
Yeah.
What differentiates your system from others is the ability to then use magnets, which I imagine would be a fairly standard
Yeah.
process in the recycling industry.
Yes.
To withdraw that silver ink element,
Yeah.
whereas a traditional RFID tag or electronics would, as you say, would then go through and contaminate that waste,
Yeah.
which would then be forced into incineration rather than true recycling.
Yes.
So yeah, another fascinating example, different industry, packaging industry rather than electronic PCB.
Yep.
But obviously with the new packaging regulations coming through, in particular from Europe,
Yes.
and the ability to effectively design for disassembly,
Yes.
and then design for segregation and design for recycling, there it is in practice.
Yes.
Brilliant, thank you. Back from the lab, been through the entire process, how to formulate the product, how to test the product, how to print the product, how to recycle the product. Couldn't get better than that. So we're going to hit the road in a few minutes, but before we go, the most important thing is basically a call to action. There are engineering companies out there right now heavily focused on circular economy in both electronics, manufacturing, packaging. So the question is, what do people need to do to get involved in this? Where are they going to find you? Where are you going to be? What's the next step for people that want to get involved in this?
Yeah, so if you'd like to get involved, the easiest ways to do it is to come and talk to us. Either reach out to us. We've got our website, web address, email, LinkedIn. Hannah's very, very good at putting lots of content out in terms of our progress on LinkedIn. So there's always a good place there to follow along with what we're doing. We'll be at a couple of trade shows over the course of the year, mostly printed electronics-based ones, because for us, that's our kind of bread and butter. And just get involved. There's lots of opportunity to work with us. We're quite happy to kind of explore new ideas and explore the potential of what we're doing. We are still quite a small team, so we are fairly not stretched, but we have a limited capacity for projects, but we are willing to listen to new ideas and always interested to try new things.
Well, and as members of the Sustainable Engineering Alliance, obviously we'll be keeping a very close eye on how this technology is evolving. Wherever we bump into you guys at shows and seminars, we'll come and interview you, and we'll make that part of our podcast series. We'll be writing about this technology on a regular basis. We've written about the core technology now, and soon we'll be moving in, hopefully, to case study-based type work where we're seeing this technology used in applications. So once again, thank you, James and your team, for looking after us today and giving us that guided tour, hands-on, boots on the ground stuff.
Yeah.
Brilliant. Thank you, James.
Brilliant. Lovely. Thank you.